Hello, my name is Katrina Turner, and I am going to present the NetSage Measurement Framework. This project is led by Jennifer Schaaf at Indiana University and includes collaborators from the University of Hawaii at Manoa and Lawrence Berkeley National Lab. Funding for this project was provided by National Science Foundation Award 1540933. NetSage is a unified, open, privacy-aware measurement, analysis, and visualization service designed to address the needs of today's research and education data sharing collaborations. It was specifically designed to look at network traffic from NSF's International Research Network Connections program, which includes networks to Europe, Asia, Africa, South America, the South Pacific, and Australia. The NetSage Measurement and Analysis Framework was developed to support understanding research data movement by collecting a broad set of monitoring data from various resources and visualizing that data using performance dashboards, which are specifically designed to address the analysis needs of stakeholders. NetSage is unified in that it combines data from a variety of sources into a single unified view. It is open in that the data collected are meant to be widely accessible, with performance dashboards open to the public at netsage.global, and also that the software developed by the team is open source. It is privacy aware, as it contains no personally identifiable information about individual hosts or users of the network. NetSage test points are a collection of software and hardware components that gather active and passive data into records. Passive data includes SNMP, flow, and tstat data. SNMP is generally collected every 60 seconds. Flow data is collected using tools like NetFlow, SFlow, or IPFix, and sampled at between 1 in 100 and 1 in 1,000 packets. tstat examines the packet headers for the data flowing in and out of Instrumented Science Archive and reports TCP statistics for each flow. It is not sampled. We use perf sonar for active measurements of throughput, latency, and loss. The throughput tests are only run every few hours for minimal impact on the production data transfers. The loss and latency measurements are run continually. This data is then sent to the data ingest pipeline. The 5-step pipeline filters those records and adds additional tags before de-identifying the data. The records are then stored in the NetSage archive, a centralized storage framework consisting of a time series data system, TSDS, archive, and an Elasticsearch archive. Performance dashboards built with the open-source Grafana analysis and visualization engine access the records from the NetSage archive to present visualizations to the stakeholders. NetSage's user interface was designed through a process of immersive empathic design where initial stakeholder questions are turned into storyboards, which are presented back to the stakeholder for feedback. Stakeholders include IRNC resource owners and operators who wanted to know the status of the resources, collaborative research teams trying to understand resource use and how their data transfers would behave, engineering staff to ensure effective resource use, and funding staff to understand who uses the resources. With sufficient feedback, an initial software prototype was implemented. Then, through demonstration and surveying of broader collections of stakeholders, the prototype was further refined. Often this process sparked new requests for features and visualizations. Questions that end users typically want answered are incorporated directly into the user interface design as a way to launch into the various dashboards. Dashboards summarize bandwidth utilization, latency, loss, flow patterns between organizations, and scientific disciplines. Dashboards were implemented primarily in Grafana with additional charts developed in D3, Chart.js, and Leaflet. From the netsage.global landing page, you can navigate to the various projects NetSage is a part of, including the IRNC deployment. When you first arrive at the NetSage portal, You see the bandwidth dashboard, which gives a broad overview of the network and answers the question, what is the current state of the network? The default time is set to the last 24 hours, but this can be changed to go back further in time. For example, if I look back to January of 2018, you can see a change in the NEAR network when the Department of Energy network operators added the NEAR circuit to the set of network resources that supports data transfers related to the Large Hadron Collider. In this particular case, dashboards were able to show this change before the email notification was sent to the resource owner. This example shows how NetSage can be used to observe unexpected changes in network usage and prompt further investigation. If I want to look at a new dashboard, I can use the hamburger menu at the top left. Notice the menu is organized by the end user questions. I could take a look at what are the top flows by country. On this dashboard, we can select a country, we'll choose the United States, and see what countries are the top sources and destinations to and from the US for the selected time period. We can see various metrics like total volume of flows, number of flows, and peak and average rates between countries. Tables like these are common across the various dashboards displaying flow data. If we scroll further down, we see the top pairs of organizations exchanging data with the United States and a Sankey graph visualizing the distribution of data volume across the top countries. We also have other usage statistics on ports, protocols, and sensors. If I wanted to know what flow data looked like for a specific science discipline, like high-energy physics or astronomy, I would click What are the flows by science discipline? This takes me to a dashboard that shows flows that are tagged as being related to a specific science discipline. Let's choose astronomy. Notice on the map, we see pairs of organizations exchanging flows tagged as astronomy data. These labels come from the Science Registry data, which is one of the unique things about NetSage. It allows us to view flows by science discipline and project rather than just locations and organizations. If we scroll further down, we have a Sankey graph that visualizes the distribution of data volume amongst the top pairs of organizations exchanging astronomy data. Further down, we also have a table summarizing all the science discipline data. As another example, staff members for the Transpac 4 project used NetSage to understand how adding a new 20G connection between Guam and Hong Kong would affect traffic. The flow data dashboard shows that the top pair of organizations transferring data over the new connection was KISTI, the Korea Institute of Science and Technology Information in South Korea, and the Computer Network Information Center, CNIC, at the Chinese Academy of Science. A deeper investigation showed the traffic path to include South Korea, Hong Kong, Guam, Hawaii, LA, Seattle, Japan, and China, which was clearly not intended. In other words, traffic that should have been able to go directly from China to South Korea was crossing the Pacific Ocean twice, resulting in significantly decreased performance. A discussion with the network engineers overseeing different parts of the path determined that the routing preferences were incorrect, and the problem was resolved. In late 2018, there were some unusual flows over Transpac 4. Transpac 4 is the IRNC project that supports connections between the US and Asia. Engineers for Transpac 4 used NetSage to identify an unusual pattern of behavior where every 10 to 12 days there was a significant increase in the data volume over the resource. On the flow analysis dashboard, we can see these peaks in traffic during the given time period. This dashboard allows the user to dive deeper into the data for a given time period. It was discovered that these peaks were due to an astronomy very long baseline interferometry, or VLBI, project, periodically sending data between the Radio Astronomy Institute in Italy and the Kashima Space Technology Center in Kashima, Japan. The workflow for VLBI applications involves several geographically distributed radio telescopes that are all aligned on the same celestial object. In this case, all located in Italy, sending their data to a collector site, in this case, in Japan. Here's an example of how COVID impacted the networks. In March 2020, many U.S. universities put in place travel restrictions due to the COVID-19 pandemic. This dashboard shows individual flows between Zoom and other organizations. Here is a NetSage heat map for data transfers to and from the Zoom video conferencing hosting site during the timeframe where IRNC institutional use of Zoom changed radically. The heat map shows data volumes starting in February 2020 that increased on or around March 12th, when many U.S. universities declared that researchers could not travel. This was followed 10 days later by a decrease, likely caused by a combination of institutions shifting to spring break and institutions issuing work-from-home directives, so the traffic shifted to home networks, not IRNC networks, and Zoom shifting some of its hosting to use cloud services not at their IP space. This is one example of how longitudinal data collection can provide broader context for changing resource use, especially in unusual circumstances. Finally, let's take a look at one of the newer dashboards that was created based on the user question, who are the top talkers over time? This dashboard displays a bump chart of the top organizations sending and receiving data and allows us to see how their rankings change over time. The default number of organizations to display is 10, but the user can change this to narrow their field of view. The user is also given the option to select a set of organizations for themselves to see how they compare against each other over time. This dashboard is currently set to the default of all organizations. Dashboards like this one stem directly from conversations with our end users. There are a number of other network monitoring efforts, but the majority were developed primarily for use by a network operations center to provide a view for a single network provider to understand and address network outages. NetSage, on the other hand, was developed for a broader set of users and to be able to analyze network performance related to data integrated from multiple networks and resources, primarily to understand performance issues and performance degradation, not outages. Particularly noteworthy is the community-driven science registry, which enables the identification of specific scientific flows. In the short term, we are developing additional visualizations as well as continuing to add more data to the science registry to be able to better reveal network use patterns of scientific applications. For the longer-term work, we are interested in adding alarms and alerts and exploring adaptations needed to use NetSage in a campus environment to better meet the needs of research collaborations. This will likely require a different privacy model, as the dashboards will not be able to be public and the granularity of information will need to be much finer. Overall, core NetSage development will continue to be funded in part by NSF through IRNC and other projects at least until 2022. It will also be partially supported for the foreseeable future via third-party deployments with the Indiana University Global NOC. Thank you for your time. I invite you to explore NetSage for yourself by going to netsage.global.